All right, so let's go, right? I start to about A. Again, this is from the handout, right? So they said A is increasing gently, velocity increasing. So we had a nice positive curve, then uniformly. So it was A to B. Then uniformly was a straight line. That's a straight line, right? That's not as number. That's zoom out a little bit there. Right, uniformly to C and then decreasing. So you have to draw a negative slope. Remember, there's a displacement time graph earlier, but we can still show velocity on it by allowing the gradient to change, right? There's a curve here earlier. Right, now we reach D, then D to E, velocity is 0, so we set a straight line. Right, this is where we reach. Right, now, nice. From E to F, the velocity is negative. What does that indicate? If the velocity is negative, it indicates what? A change in direction, right? And it's slowly increasing. So your graph will look something like that. Hold on, the graph will look something like that. And that'll be it. All right. So that's an increasing negative slope. F to G, the velocity is negative and uniform. So what to do? What to do, Alia? They said uniform. So what to do? Straight line, right? And negative. So it means the gradient going down like that. Oh gosh, what do I do now, boy? That's space. Right. G to H. What is said happen from G to H? Take a little read. G to H is what? What is said about G to H? Displacement is negative and velocity is negative and uniformly increasing. So if the displacement is negative, then we have to go below the x-axis. Everybody okay with that? And then they said velocity negative and uniformly increasing. So what to do? Straight line? So that's G to H. So we reach H now. Right. Next one, H to I, the displacement negative, velocity negative, decreasing gently. So what to do? Curve it inwards a little bit. All right. And then that's H to I. And then I to J, the displacement is negative, velocity positive. So what will happen now? What will the gradient look like in Daniel? Velocity is now positive. Will the gradient be negative or positive? Yeah. So I'm going back up now, right? So I'm going back up. That is until I reach G. And then lastly, J to K, displacement negative, velocity decreasing until it reaches 0. That's the K there. A, B, C, D, E, F, G, H, I, J, K. Okay, that was the homework there. The graph should look like that. Yeah, there now. Ready? Let's go again. Everybody have it? So now we're going to change to a velocity time graph now. Right? Everything else from the graph that we spoke about last day, right? Now we're going to focus on velocity time graphs. Right? So a velocity time graph, it shows how the velocity of an object varies time. We know that the greater the velocity of the time graph gives acceleration. If the acceleration is constantly changing, then the acceleration at a point is the greatest tangent. Yes. Are you okay with that? If the acceleration is uniform over a given time, then it's very constant, and the acceleration is just simply found by finding gradient. Everything from point back, right? Area under the graph gives us gives you what? Area on the graph gives you the distance graph. Nice. I just really shoot a little more up here. This is just the video. Right. So the distance traveled by an object in time. The negative and positive signs for the velocity indicate the direction in which the object is traveling. We talked about that last week. Right? One direction positive, the next direction is negative, right? Right, Asia? You sure? Nice. The negative and positive signs for acceleration indicate the direction in which the object is changing. If it's changing from one direction to the next, you will see a change in the acceleration sign. All right? When both A and B are in the same direction, velocity positive. When A and B are in the opposite direction, velocity is decreasing. Okay? So what we have to do here now, on the same graph here, we have to try to sketch what happened here. Right? So let's read it through and then we're going to try to make a sketch. Right? Same thing, A to B to C all the way down. So A to B, the gradient constant, the acceleration constant, and the object accelerates uniformly from rest. In fact, let's do it one time. Draw those axes there. Velocity time graph. Yeah, no, the last one was displacement time graph. This one is a velocity time graph. Right, just to the axis, remember it's a velocity time graph, gradient is acceleration. All right, let's go. First one. So draw this on your graph. A to B, gradient constant, acceleration constant, object accelerates uniformly from rest to B. So that pass, please label A and B and B and thing, right? Label everything. Start from rest, start velocity B. Right, next one. So A to B is a straight line, right? Yeah?
Yes, sir.
Right? And just make sure it goes up to the velocity V, right?
So I think fast. Is by saying that. You even don't think so.
Next one, B to C. Oh, sorry, but this thing, I want to make it small so because B to C, gradient is decreasing. How do you draw a decreasing gradient? Curve, right? That's okay, decreasing gradient. And the velocity is still increasing, but at a lower rate. So that's from a right, you might see a few other. Right, next one. So that's B to C. So far you should have something like this. Right, start at A, straight line to V. That's a V, right? And then it decreases. Right, so the velocity is still increasing, but at a lower rate. Next. That's like a summary. A to C is positive, B positive, velocity increasing, right? So there's no more information. Now C to D. You'll see that? C to D, the gradient is 0, velocity constant, acceleration. Draw C to D. Good job, Connor. Now C is C to D. Correct.
Excuse me.
Right? That's C to D, right? Now D to E, gradient constant, acceleration constant, but look at it there. Look at what's happening. The acceleration is now negative. How are you drawing that? It's time to go down. Acceleration is negative, velocity positive. Adam, all here. Grade one. Are you done? Are you next grade one?
Grade one, yes.
Not grade one, I mean Mikhail, sorry. Mikhail and Mikhail, right?
So if you do a question,
Who's that?
Sa sa class. Siya may sa.
Aisha?
Yeah.
Huh?
Yes.
The lie.
Sila yung siya si Luke ng Titan. Asher Luke ng Titan mo.
That 96.
Sa hijab lo ay lang sa to.
So what's the sense to just feel yeah?
Ang club ya.
Yeah.
Yo.
Alright. Next, so we reach D to E. Next one. Sorry. I skip out one. E to F. Eta F. Join eta F. Join eta F. Velocity is 0, right? So where will that be?
Yeah.
On the x-axis, right? When you finish, go FG one time. FG one time. Or let's put in the values like FV2 and V3 and thing, right? Right, so F to G, gradient constant, acceleration constant, A is negative, B is negative. Velocity is increasing, object accelerates uniform. Eta F will be allowed here. Plus it's 0, right? Then do F to G. Oh, you come back up already.
Was I? Listen.
Oh, you finished your thing already?
Good boy.
Well, but look like that, be cool, so be careful. Most of them cuts, most of them are.
So you must say this to this. So I'm putting it thanks to come.
Right, that's F to G. And last one. Sorry, last two. Last two. Where we stop? F to G. G to H. G to H. G to H. And then H to I.
I spoke to him before. I can reach it, right?
And last one is H to I already. Yeah. H to I. And then all I want to do for me is just put in A1 and A push-ups. That should be it two. Put in A1 and A2, please. Put in A1 and A2 in diagram. And then I'll go back and show the whole thing.
I'm going to go my phone. That is like the young person. Yeah.
Finish. Put in A1 and A2 in diagram, right? So let's go back to the whole thing there. Right, so we're going from A to B. Right, that's the B, that's the A.
It's not
Yeah, I just got to and make sure we get you. I just got to go and make sure we both have the same thing. Right. A to B, the velocity here is B. Right, and then we go in B to C. Right, C was what? A velocity of B, V1 of V2 or something. V2. So this is V1. This is V2. Then C to D was here. Right, then D to E all the way down here. E to F is here. Right? And then I think it had F to G. And that would have been a velocity V3, right? All straight lines, all no curves, huh? E, F, except for B to C, everywhere is straight lines. E, F, G, H, going to I. Here's A1, here's A2. Well, yeah, well, you want the average. If it was a curve, you had to use the average one. So your A1 is there and your A2 is there. So if I ask for the total distance traveled, add up A1 and A2. If I ask for the total displacement, it will be A1 minus A2. Why are you minusing A2? Because A2 is underneath, A2 is below the axis, right? A2 is negative. Was it? Sure. All right. So those are the things that we need to know about time graphs, right? You have to be able to take info and draw any time graph, displacement time graph or velocity time graph. All right. Right. Let's try 2 questions here, and then we're going to apply equations of motion, right? Lastly, I showed you the proof for the equations of motion and how to get all of them, right? Right. Try to sketch a graph up. Sketch a graph of the following. A ball is released on an incline. Yep. A ball is increased on an inclined plane. Yeah, a ball is released on an inclined plane. Comma, strikes the block, and rebounds upon the slope. Sketch a velocity time graph and an acceleration time graph for that scenario, right? Yeah. We said, okay, a ball is released on an inclined plane, strikes the block, and rebounds up the slope. Yep. Sketch a velocity time graph and an acceleration time graph. All right, so we have a little scenario here to look at, right? Hmm? You're just forward. So you have a block, you have a ball, the ball going down and bounded. I want you to try to sketch the velocity time graph, and then I'm going to help you with the acceleration time graph. This comes from this. So we need to have them under each other, right? Copy it down.
So you're gonna know what's called, sure. Oh, I guess it.
Try that quick. Sharon, Tyrese, Jordan, Cheetah. Oh, Cheetah, no. Emma. Emma somewhere. Joseph. Hamlet. Hamlet. Severa, Dante, Nathan, Mikhail, Ridwan are here. Mutabi, she not here, she didn't come out. Ashad, what's the last name? Here. Amit. You want to beach? Christian. Yeah. Another idea. Adrian. Naveen. Mikhail. Mikhail, that's a big cheek off, right? Eden. Ethan. Yes, I didn't put it out. Adam, are you done? All right, come and help me here. Nathaniel, Keshav, Zara. All right, 2 weeks, yeah. Huh? We'll get that to nothing. Amira. Amira, yeah. Judah online, Reese. Joseph, give me wrong thing. Right, some wrong here. Right, what he did here. Right, and something I forgot to mention, we ignoring every system. Whenever you ignore every distance, all your graphs will be straight lines. When you include, the graph have curves.
No, I think you got it.
Right, but here have a little mistake, right? Sort of close, sort of close. Right. What y'all think?
So like this.
Full line straight? Yeah, but if it all straight, then it's saying what?
And he said,
Right?
okay.
But let's see what it got.
Think I wanted from my aspect that just like
Right.
And then okay.
All right. So, right. So what you will recognize here is that initially the object has a velocity v going downwards, and then it changes direction when it rebounds. So one direction positive, one will be negative. Okay. So if your first direction positive, it has to be up here. Okay. So it starts from rest. Right? And then what will happen after that? And then when it rebounds, direction changing. So how do I get that grade to be negative? Can the velocity? So down is positive. Are you okay with this? It could also be down is negative. That can happen as well. Right? But my question is, if down is positive, and up is negative, where do I put in negative part? It will have to be down here. Right? So as soon as it hits, I'm trying to make the areas the same, right? We are assuming it's elastic. We're trying to make the areas the same underneath here. So that's one version of it. Are you okay with that? What do you think? What do you think? Right? And now, what you recognize happening with gradient here and here? Gradient constant, right? So gradient represents what? Acceleration. So what we can see happening here? Positive acceleration. And then going back up is, right? This line is important, they must overlap, right? So this is G, negative. That's okay? Right? At this level, acceleration will not change. Every single thing that we do, acceleration constant. Okay? Are you okay with that? So this kind of popular, that's why I gave it a scenario, right? Ready? One more. A particle is projected. A particle is projected vertically upwards. A particle is projected vertically upwards. With a velocity of 50 meters per second. Huh? A particle is projected vertically upwards with a velocity of 50 meters per second. Huh? Same question? Kindly value, but I have to give it graphs. 50. A particle is projected vertically upwards with a velocity of 50 meters per second in a uniform gravitational field. In a uniform gravitational field. First up, neglecting air resistance. Same value, Stephen, right? I mean, the same value last year. Yeah. Neglecting air resistance, sketch the velocity time and displacement time graphs. Sketch the velocity time and displacement time graphs for the motion of the particle. For the motion of the particle.
Huh?
Get exacting every distance. After that, test the graph of the velocity time and displacement time graph. Sketch the velocity time and the displacement time graph. Huh? Right? Last day I gave you the values for this, right? For which one? Yeah, just your displacement velocity underneath. Right, but before we do it, right, I wanted to use the values from last class. So you say you have to recalculate it over. So if I can say, I think it was time taken was 5.1 seconds. 5.1 and total journey was 10.2. I have 5.1.
Yeah.
5.1 and total journey was how much? 10.2. And what was the maximum height reach? 127. Okay, nice. So the maximum height was 127. Time for the whole journey was 10.2. So I would like you to sketch the displacement time graph and the velocity time graph. Catch it quick. Catch the graph. Particle thrown vertically upward. Right? I want the displacement time graph and the velocity time graph. If you work on the velocity, as I gave you a velocity, I throw it upwards, right? So I want values, right? Daniel, I want values in it, right? Got that? Catch the graph. Yes, so throw it upwards and then come back up. How the displacement time look? The max value is what? 127. And the time it take to reach the whole journey was 10.2. So here's 5.1. How to look? Start from rest. And it will reach a maximum displacement here, right? So would it look something like that? Yeah? And then when it reach max height, it will come back down. Catch the velocity time graph now. Different. This one started from rest. That one's next one started with a velocity of what? 50. Get people up quick. Right? So it moves off with a velocity of 50, but you are assuming there as well.
Yes.
Right? But you're also assuming that upward positive. Let's think going upward first.
So velocity negative.
So
If
what
we
will
are
happen?
negative really.
You're gonna but that could work. 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 Positive to zero. That'll give you the negative gradient. Right? So we can do something like this. Start with a velocity of 50. Then it goes upwards. Right? That will be a velocity of to zero. Start at 50 to a velocity of 0. When it reaches 0, it'll come back down, right? So then it will speed back up, providing it perfectly elastic. It will come back down to minus 50. All right? Right? Again, same thing. A1 here and A2 here should be equal, right? Right? If you do the next way, would also correct as well, right? Okay with that? So these are your time graphs. These are the two most popular. By the way, if I ask for the acceleration graph, what does it look like? Something like this, something like this in reverse, right? Negative, positive. All right. So the next thing we're going to look at after the time graphs, we have to go into something called projectile motion. All right. I'll keep it really steady, right? No, not next class. Huh? Oh, they got a long break already. Oh, they got a whole 15 minutes to play card.
So
Who went?
when you think about it,
That was one time I used to have it later, like as a habit, like half 7 or so. As a habit, like after 5 to half 6, I had to have it half 6 to 8. What's up? Well, that's one time it's had to be late. No, but don't be wrong on a Tuesday. Huh? No, I can just give all the half an hour break and then we start. We can just finish 4, half an hour more. So I'll give you a good break. All right. So I want to move on to something called projectile motion, right? But before we do that, I just want to go back over the equations of motion. What were the equations of motion again? V is equal to U plus AT. V squared is equal to U squared plus 2AS. S is equal to UT plus a half AT squared. Right? S is equal to U plus V by T. It hardly ever uses. Right? S is equal to V by T. Right? what you will recognize is that these three equations are affected by acceleration, right? These are affected by acceleration. This one here, not affected by acceleration, right? Are you okay with that? So these equations here, affected by acceleration or affected by gravity. Okay? So what we're going to attempt to do now is we're going to take a look at two things closer. We're going to take a look at vertical motion, and we're going to take a look at horizontal motion. In horizontal motion, it's not affected by gravity. Gravity only affects something moving vertical, right? All right. Last thing we're looking at, something called projectile motion, right? That's the only for 15 and you'll get. That's simple, right? So projectile motion, we get, right? Projectile motion is where if we have the ground, we shoot a particle at an angle to the ground. So it's at an angle theta with a velocity of u. That's okay? So at an angle to the ground. What will the path look like? Right? It will begin to project outwards, and then because of gravity, when it reaches its maximum height possible, it will begin to go back down until it reaches a displacement of 0. That's okay? Throughout the entire journey, the velocity is going to keep changing. All right? So for example, at this point here, it has a new velocity v, right? But we learned that anytime something is at an angle, it has what? Like for example, if you have a force at an angle theta, it has what? Right, it has two components. Because it's moving diagonally, it has a horizontal component and a same thing happens here. It has a horizontal velocity and a vertical velocity. Adam, you okay with that?
Yes.
Are you okay with it?
Okay.
So if the particle has a velocity v here, it has a horizontal component and a vertical component. Right? And then it should also have a what? A displacement. So if it's here, it should have a vertical displacement and a horizontal displacement. We have to attempt to find all those things. Okay? Sketch a diagram. Sketch a diagram, and we're gonna find everything. while it's drawing, if you remember how to resolve components. So if you remember how to find your horizontal component, right, Nathan? So Nathan, you remember how to resolve? So if here is u, the x is what? Plus or sine? Adjacent, right? So if you have the angle adjacent is here, so that's u cos theta, and the next is what? U sine theta. All right? Joseph, you remember what we could say about horizontal motion again is not affected by what? Not affected by gravity, right? So horizontal motion not affected by gravity. So what does that mean? If it is not affected by gravity, will it ever change it? So we're using these, but will it ever change? No, because not to change it, right? So therefore, this here will always remain constant. So therefore, your horizontal components are what to note that your horizontal component for velocity is always constant. Are you okay with that? Because gravity not affecting it, it's always going to stay constant. So as the object moving, its horizontal component is always constant. So my question is, what is Vx? Adrian, what do you think is Vx? Yeah, this one here. Now, what we just say? Horizontal component for velocity always remain constant. So what would be Vx if you know what Ux is? Same thing. So it will be U cos theta. That's okay? But Taniel, here's the problem. The problem with Taniel is that I want to get the vertical component. It's all constant, sorry. Yeah. Huh? Yeah. Yeah, Nathaniel. So the vertical component now, Nathaniel, is affected by what? Is affected by vertical affected by gravity. So it would change, right? So it wouldn't be this anymore. How fine. It would no longer be u sine theta. What would it be? What do you think? What we will do? Any ideas, Nikhil? Hmm? You're right. Nikhil, what do you think? Yes, Nadam? Michael, so the problem is I want to find this, but I can't use this because this value changing. This is the initial component. What can I use or how can I find this? I gave you something at the beginning of the class that will help you. Sorry, the beginning of this here, that will help you. Give you all these. Right? So can we use any of these to find P? Yeah, we could use this or we could use this. Right? Since we don't know S, we gotta find that later. Let's use this here. Right, Emma? So we want to use so to find Vy, we are going to use V is equal to U plus AT. Right? But remember, if we have to use this, then everything must be V, right? Everything must be vertical. That's okay? So I want to find the final vertical velocity, that's Vy. What is the initial vertical velocity? U sine theta. Yeah? Ashad? You sure? Ashad, what is the acceleration vertically? Negative what? Negative gravity. So at any point in time, I can find the velocity here once I know the initial, the angle, and gravity. And well, how long until? Daniel, am I making sense? When I'm making sense, tell me. You okay with this?
Yeah.
Right. But the vertical component changing, right? Because of acceleration. So because it's changing, we have to find, because gravity affecting it, right? We have to see how much the gravity affecting the initial velocity. That makes sense? So as the initial velocity, as it's moving, gravity either slowing it down or making it larger. All right? So here, or here, or here, each one of these equations showing you that acceleration affecting whatever you want to find. Okay? So we want to find final velocity V. So the only thing that we can do is use here or here. We could use the initial velocity, we could use the acceleration vertically, and if we have displacement vertically, we could use this as well. So because we're going to need this later on, I say ignore this. We're using this version here. So to find the vertical velocity, we're using the initial vertical velocity, which we have. We're using the acceleration vertically, which is gravity, and then, well, minus time or something later on. So at any point in time, I can find the vertical velocity. That's okay? Dante? Okay with that? Right? So at any point in time, I can find the vertical velocity. It becomes easier when we use numbers, right? But I want to test the proof behind it first. So if I know the vertical velocity, Ashad, if I know the vertical velocity and the horizontal velocity, how do I find the actual velocity? How do I find V? I have Vx and Vy. How do I find V? Pythagoras theorem, right? Square root of Vx squared plus Vy. That's okay? Emma, I just put some help to find X and Y and we done. Just think about it. X is what? Horizontal or vertical? Horizontal. Y is vertical. So while you're writing, and that's why I'll help how to find X and Y. Once you hear vertical earlier, these three things come to mind. Once you hear horizontal, this comes to mind. If you wasn't paying attention all the time, all I want you to focus on is vertical, horizontal. Emma going to help us do one and then add on the last one. And we're done. How do we find X and how do we find Y? Hi, on the lemonade feed, I'm coming over this. See? All is B, right? Yeah, use X and Y. Yeah, sorry about that. Yeah. I would have changed all to Y, sorry. Thanks. Now, may I use VB and VB? Need to know goals for Am I ready? Yeah, right. I'm glad you're ready. So you want to find horizontal displacement. So we know we're using this. That's okay? So remember, if you're using horizontal displacement, then this must be horizontal. This must be horizontal. Do I have to put time as horizontal? Time is scalar, right? So now x is equal to, we use that same thing there. Sx is equal to Vx by t. This is what? This is your horizontal displacement, which is x. What is Vx? U cos theta by t. That's okay? And who's the next person? Adam. Adam, how we getting y, right? How we getting y? How we getting vertical displacement? Which one of those are gonna use? Huh? U sine theta. Yeah, but remember U sine theta is initial velocity. We want to get displacement. Right? Which set of equations are you using? These two or this one? First two, because we're dealing with vertical motion. Which one of these will help you find us? Third one. Why didn't you choose the first one?
Because
Third one of us. You could also use here. You could also use here, but this is better one. I'll show you why later on. Right. So you're using S is equal to UT plus a half AT squared, right? Can I fit all that there? I can't fit all that there. So here's Y, and here's Y. Can you tell me what UI? U sine theta, nice. Question I've chosen. By what? By T. And what is EY? EY is acceleration vertically. What's that? Gravity. And going up first, so it will be fine. That's it. That's all. Right? You all did projectile motion, huh?
Yes, we do.
Huh? Yeah.
Yes, we do.
Right, one.
So we can.
Wait, another.
We see how close.
You will end on this?
So woman, after
Right.
15 minutes.
Right? Anyway, but you'll follow how I use the equations of motion here.
Yes.
When I put numbers in it, it becomes easier. But what I'm trying to show you here is for every single thing I use an equation of motion. So you don't have to learn this afterwards, you know. All you have to learn now is how to use those things properly. Right? So I want to point out again that when I use the equation of motion here, I use the vertical initial, I use the vertical acceleration. I use everything vertical. Here, I use everything vertical. Here, I use everything horizontal. Okay? So when they consider in horizontal motion, we consider every single thing horizontal. Okay? Most important thing from today is this, I want to learn this. Because next week, all we're doing is past papers on this. Questions on this, right? So next week, remember what we're doing, we finish in quarter third, and I'll give you a break after few. Which one? And we'll be open.